Okay, so where we left off is we had not defined the turning points yet. So what are turning points? Turning points are just where a graph changes from increasing to decreasing or vice versa. So it's when a graph is rising and then suddenly it starts falling. Okay? So that's a turning point. And something you don't know yet about polynomials probably is if it has like degree 4, then it cannot have more than 3 turning points. Okay, so let me just explain that real quick. Let's say I told you that there was a degree 4 polynomial. You would know that it would be arms up, right? So you know that much. But there's lots of questions about what happens in the middle. So here are some possible graphs. It could be like that, and it only has one spot where it turns. So it goes from decreasing and it jumps to increasing. That's possible. Or it could be arms up, like this, and it could have more wiggles. So you'd see this sometimes on your graphing calculator, maybe something like this, where it goes from decreasing to increasing here, from increasing to decreasing here, and from decreasing to increasing here. But because it's a degree 4, it cannot have more than 3 of these points. Okay, so in other words, this is not a possible drawing for degree 4. This drawing is not allowed. It's too many turning points for a degree 4 to have. What's the most number of turning points a degree 4 can have? 3 is correct. Now that doesn't mean it has 3. It could have 3, or it might only have 1. Okay? So it's 3, which is n minus 1, degree minus 1, or 2 less than that. Okay? Let me do another quick example of that. You have a question?
Yeah. Would the exception to that be a piecewise function?
Yep. We're talking about polynomials here. So if you make piecewise functions, you can make exceptions to just about any rule. You can have points on an asymptote. Okay? You just have to define it that way. Good question. Okay, let's look at another one. Let's say that I gave you an x to the 5th polynomial. Okay? You know, x to the 5th plus blah, blah, blah. What does it look like? Show me with your arms. I know I laughed at you once. I won't do it again. Okay? Sure. I know. It looks like this, right? Okay, so what are some possibilities for the middle here? Like, what might it look like in between? Well, it's possible that it's just like that. And there's no turning points at all. The graph never actually falls. In fact, it just kind of rises and then rises again. So this might look like a turning point, but it's not really. It's just rising the whole time. Okay? All right, so maybe we draw that a little bit better so you can see it. What I'm saying is, with an arrow down and an arrow up, it's possible that it just kind of connects like that. There's no rising or falling. Okay? Just rising only. That's one possible drawing. Another possibility is that there's a down arrow and an up arrow, and it does a set of wiggles like that. There's one point where it turns from rising to falling, and one where it turns from falling to rising. And then the last possibility is this picture where it goes rise and fall and rise and fall and rise like that. This is possible. So what I'm saying is it's possible that there are no turning points, no TPs, okay? 2 turning points, 2 TPs, or 4 TPs, but there cannot be more than 4 because it was a degree 5 polynomial. Okay, so there can never be more than n minus 1 turning points. That's what this rule is saying. So if I gave you an x to the 5th, like this one over here, does it have 6 turning points? No. It can have at most 4. It might be this picture, it might be this picture, it might be this picture. We don't know until we learn our basic calculus, you know. Okay? All right. But it certainly cannot have more than 4 if it's only degree 5. All right, hopefully that was clear. What would this graph look like? That's a really generic question, but what would it look like? Well, what are my x-intercepts? Let's start there. 0, what? 1 and 2. Okay, so if you make a sign chart, you could put 0, 1, and 2 on here. And we would expect since this is an even multiplicity, and this is an odd multiplicity, and this is an even multiplicity, so I'm describing the multiplicities, 2, 1, and 2, we would expect that at 0 it's going to switch signs. I'm sorry, it's not going to switch signs. At 1 it will switch signs, and at x equals 2 it will not switch signs. Okay. What is the overall degree structure of this polynomial? I've got x squared, I've got an x, and I've got another x squared. So what is it? Degree is 5. Right. So if it's degree 5, we know that it looks something like this. Right? In other words, over here it's negative, but over here it's positive. Right? If we want to study x equals 0, we already said it's an even multiplicity here, so we know that it's going to have the same behavior on both sides of 0. So this is also going to be negative. Okay? When you get over here to x equals 1, there's another root. X equals 1 had an odd multiplicity, so we expect the sign to change when it hits x equals 1. Change from what? Change from negative to positive, see? Okay, so change from negative to positive. When you hit x equals 2, it looks like we've already determined that the function is positive beyond that, and it was positive coming into that. So does this jive with this function? Yes, because x equals 2 had a 2 multiplicity, and we're not expecting a sign change here. So everything worked out just right. Okay, so remember what the minuses mean? The minuses mean that the graph is below the x-axis. So the graph for this would look something like this. Below, touch the axis, below, touch the axis and pass through. Now we're in the positives. Come back down, touch the axis, but stay above. So all the pluses mean you're above the axis, all the minuses mean you're below the axis. And this is actually a decent graph, although I still have questions. Like I have questions like, what about these points in here, you know? Like where are those at? Don't know yet, right? Okay, and then the question also asks us, how many endpoints does the graph have? But I'm really not sure what that means. I don't know what it's talking about. These graphs don't have endpoints. So let's skip that question. I have no idea what that means. Let's go to the next page. Maybe turning points? Okay, maybe they meant to type turning points. I don't think I typed this problem. But, how many turning points did that graph have? Count them. It's just where it changes from rising to falling. Falling to rising. There were 4, yeah. There were 4. Turning points, it went like this, then it went like this. So there were actually 4 turning points. 1, 2, 3, 4. So I think this meant to say turning points. Yeah, good, good. Okay. Thank you for helping me understand the question. I did not know what that meant, endpoints. All right, let's go to the next one. In behavior, you know, when the functions are all FOILed out, there's one term that's going to have the most power, right? For example, in this thing, if you were to FOIL this thing out, it would take a while, but I'm pretty sure you would end up with a 32x to the 4th plus a bunch of junk. Why do I say that? Because if you just kind of circle the first thing in each parentheses and also the leading coefficient, you basically have a 2x that's being cubed. That's 8x cubed. And then you're multiplying by x and by 4. So whatever this corner polynomial is, it definitely starts with 32x to the 4th. Okay? So what this means graphically is for large values of absolute value x, f of x resembles 32x to the 4th. Okay? So let's say you plugged in 1 million, or 1 billion, or 1 trillion for x. This term would be so powerful that the others, even though they're big, are minuscule compared to it. So this guy sort of takes over. And if x is 1 million, billion, trillion, or like a this function when x is a googol is pretty much the same as this value. So this thing dominates the function. And it's called the leading term for a reason. So anyway, we call this the end behavior model. This is called the end behavior model. And it's not that helpful in math to know the end behavior model, but at least it tells us that this graph has arms up. You know what I mean? It's x to the fourth. We know that. So that's important. If you graph this function right here, and you graph this 32x to the fourth, you know, you do like y1 and y2, and you graph them both, and you zoom way out, you cannot tell the difference between them. They look almost the same. If you zoom way, way out, and you don't look at all the little wiggles, man, they look very similar. Okay? What do you suppose the end behavior model is for the next problem here? This is part B now. Just try to pick out the leading term here. What's 2 times 3x squared times x cubed, you know? 2 times 3x squared times x cubed. What's that? Yeah, it's 18x to the fifth. Yeah. So for part B, the end behavior model is 18x to the fifth. Never give me more than one term. Your answer is supposed to look like a sub n x to the n. It's like one monomial term. Okay? And I've had you raise your arms several times today, but it would look something like that. Okay? Any questions on that? End behavior is pretty simple. All right. Let's go ahead and look at our new worksheet. Let me pass it out real quick, and then I'll do one of the problems for you. Okay, so this one is a little bit different from the last one, only in some of the questions, but ultimate objective is the same. You're trying to sketch the function. So the first thing you do is find the roots and the multiplicity. Second thing you're going to do is determine whether it crosses or touches the axis at each root. We went over that. And then the third one is determine the possible number of turning points for the function. That's new. And then determine the end behavior model. It's kind of new, not really. And then find the y-intercept. I don't think I had that on last night's. Can't remember. And then sketch it. And then the last thing is the most different. We're supposed to use our graphing calculator to estimate the max and min points that we're not sure about. Okay, so let's just run through this. So what are my roots on number 1? 0, 4, and negative 6. And the multiplicities? 0 has multiplicity what? 2, right? Because it's squared. 4 has multiplicity 1, and negative 6 has multiplicity 1. Yeah, because there's ones here that no one would write, except me. I'll write them. Okay, so we know then that p of x will cross the graph, cross the x-axis at 4 and negative 6, right? And we know it would touch the x-axis at where? X equals 0, right? Now this thing, if you look at it, it's basically negative x squared times x times x. So I'm just ignoring any constants I see. But what is the end behavior model for this? Negative x to the fourth. This just means if you were to FOIL this thing out, the very first and most powerful term is negative x to the fourth. So it's actually easier to answer part D first. We now know it's a degree 4 polynomial. And that means that there are either 3 or 1 turning points. 3 because that's 1 less than 4. 1 because that's 2 less than 3. Okay? So you get the 3 by subtracting 1 from the degree. And then you drop that by 2. Okay? Y-intercept, you just let x equal 0. So on this problem, that's just going to give you 0. So the y-intercept equals 0. 0. And then use the graph paper on the right to try to sketch it out. Do not attempt to estimate the turning points. Okay? Yet. So what we're going to do is just sketch what we know. Totally rough draft here. So we know that it passes through negative 6. We know that it passes through 0. and we know that it passes through 4. So my x scale on this thing is fine. This is 10, this is negative 10, no big deal. Okay? We know that this resembles a negative x to the 4th graph, right? That means there should be an arrowhead coming down here, an arrowhead coming down here. So that means we get a head start on sketching. We know the extreme behavior of the graph on the far left and far right. Don't get the calculator yet. Not yet. Not ready. Okay, next is the middle part. Well, we know that there are 3 roots, so the graph basically has to go through all 3 points. We've already determined that the graph crosses the x-axis at -6, so we can expect it to rise up into the second quadrant there. We know that it only touches the axis at 0. That means it comes down and just bumps the axis and then rises again. And we know it passes through the x-axis at 4. This is a very rough sketch, okay, and it is not meant to be a good sketch. I'm very curious where these 2 peaks are right here and here. I do not know where they are yet. So that's what the calculator is going to be able to help us with. Okay? So you can turn on your graphing calculator at this time. And enter the function under y equals. It is negative, and you can just type it just like it looks. You know, you don't have to like FOIL it out. Did anyone FOIL all the problems last night? Oh, I'm glad. Okay, that would be a real waste of time. Okay, type the function, and if you press graph and you have yours on Zoom Standard, that is not a very interesting graph. Okay? So it looks like we've got some activity up top that we're not seeing. So let's change our our Y max. So I was going to press window and just change Y max to 100 to see what happens. So I'm changing Y max to 100. Let's see if that does any better. It's a little better. I got at least 1 turning point in that picture. I actually have 2 of them. There's one at the origin and there's one in the first quadrant. But I still would like to see the top of the graph. So let's do another zoom. Another window. And let's make the Y max. Why don't we make it 300, see if that helps. There we go. Much better. 300. I just need to be able to see it because I plan on finding these 2 points right here, you know. I need these points. I'm pretty sure there's a turning point at the origin, so that's not a big deal. Okay, so to get those, we'll just use our max feature. And so you just press second calc. Okay, and go to maximum, option 4. And I know that that first peak lives somewhere between -6 and 0. So instead of using the scroll here, we've been just typing. For left bound, I'm just going to type -6, enter. For right bound, I'm going to type 0, enter. And then when it asks me to guess, I never do. I just press enter a 3rd time. It found it. It's at -4.29, comma 260.9. So I'll write that on here under where it says turning points. So -4.29, comma 260.9. Nearest hundredth, right? Nearest hundredth. Okay. Let's go back to our graph. I have another point I'm interested in, this other peak. So let's run through that wizard again. Second calc, maximum. This time I know it's somewhere between 0 and 4, so left bound 0, right bound 4. Guess, no thank you. It's at 2.79, 82.79. 2.79, 82.79. So I'll write my answer a little bigger so you can see it. I got -4.29 and 260.90. 0, 0 is obviously a turning point. I did not need the calculator's help for that one. And there's a turning point at 2.79, comma 82.79. Now the last thing I need to do is just tidy up my graph. Okay? Because right now it looks like my 2 maxima are like y + 1. Okay? That's not right. So I think what I'll do is I'll just make the top part of my y-axis represent 500 right here. And that makes this 500, 400, 300, 200, 100. So every other space is 100. And now right on top of this graph, I'm going to graph the updated and more improved final draft here. So I believe the graph should look more like this. This red point should actually be up at 261, and it's at negative 4.29. So that'd be like right about here, actually. Actually, I have it a little too close to 300. Let me lower it. So it needs to be at 261 and at negative 4.29. Okay, so much for my first draft, right? Also, so much for the notion that the maximum will be halfway between the roots. Look, it's actually closer to this root than it is to this one. Okay, so this red point, I'll label that one A. That's the negative 4.29, 260.90. And then the other point was at 2.79, 82.79. So I'm actually not too far off with my original sketch. That would be right about in here. So this is the point C, and B is just this one at the origin. So I'm titling these now A, B, C. And I'm going to redraw this graph. Actually, don't erase your old one for me, okay? I want you just to draw a new one. So let's go ahead and sketch in a brand new one here. See if I'm allowed to pick a different color. No, I guess not. Okay. Well, anyway, this is my final draft. Maybe I'll make my old one like dashed or something. Or I think I'll erase my old one, but you guys go and keep your old one, okay? Just make yours more bold for the final answer. There. Now it's a little more accurate. So we had to use our technology a little bit because we didn't know how to get those turning points, and you honestly won't know until chapter 4 next year, calculus. And then you'll be able to do it without any calculator at all. That's number 1. You're going to do 2, 3, and 4. Okay? And then I just want to tell you where we're going as a chapter. We're going to jump next to 3.7 and 3.8. That's Monday and Tuesday. Okay? And honestly, the only thing you're doing that's any different at all is this, guys. These will not be factored. So we will have to factor them first. But this will all be expanded out like that. We're going to try to get it all factored so that we can do this. See? So we need to start from scratch and factor everything. That's 3.7, 3.8. That's Monday and Tuesday. Wednesdays are quiz. Fridays are test. Okay? And everything from here on out, the rest of the chapter is review. Because you did synthetic division, all that stuff for factoring last year if you took honors to algebra 1. I mean honors algebra 2. So.